Good afternoon, everybody. Welcome to the next session. You're privileged to hear Irit Katriel here. We'll be talking about the CPython compiler pipeline. This session is scheduled for 30 minutes. There may be time for a question or two afterwards. And if not, Irit has graciously volunteered to meet with you outside in the hall afterwards. So let's give her a big hand, and here we go.
Thank you, Ned. I'm Irit Katriel. I'm a Python core developer, and I work at Microsoft on the faster CPython team. I'm going to talk today about some work I did over the last couple of years on and off on the Python compiler. I refactored it and I exposed a few more stages of the compilation process to Python. So I'm going to talk about what I did and what the motivation was and why this came up now. So when you run a program or an expression on the Python prompt, I'm assuming you probably know this. The code first gets compiled to Python bytecode, and then that bytecode gets executed on a stack machine. Now, you can also execute on the prompt each step separately. We have a built-in function called compile and another built-in function called exec, and you can compile your code, get an object that's called, the type is code object, and it wraps the Python bytecode with some metadata that is needed to execute it. And then exec will take this code object and execute it as if you're running your program. So already you see we have some kind of pipeline here with two stages. Now this talk is about the first stage. I'm not interested in execution at all. I'm not going to talk about it anymore. And this first stage of the compilation, you might be familiar with these sub-stages of tokenizing the bytecode to get the source code to get the program's tokens, and then the parser that builds an abstract syntax tree, and then the compiler that takes that and builds a code object. These stages are also exposed to Python for a long time now. So this is not new. And the part that I'm going to talk about is this part, going from an abstract syntax tree to code object. Now, I will cover the existing stages a little bit just for completeness, but really the focus will be on the refactor of this last part into sub-steps. So the new compilation pipeline will look like this. The shiny bright blue is the new steps that I added that are exposed to Python. So the new pipeline looks like this. From source code, we tokenize, then parse, then we have an AST. We optimize the AST. Then there's a code generation stage that produces an instruction sequence. That is, these are not bytecode instructions, but they are of the same flavor. We call them pseudo instructions. And then we optimize that instruction sequence, and then an assembler creates the bytecode and wraps it into a code object. So that is the new pipeline. That's what I'm going to describe. And so just remember that the bright blue are the new stages, and the darker blue, those are things that already existed for a long time. So what was the motivation for this? And in Python 3.11, we have these two stages. In 3.13, we have this refined pipeline. In 3.12, it's somewhere in between. It was kind of work in progress. The motivation for this was unit testing particularly of the peephole optimizer, and I'll talk about it a bit. But there was also a secondary motivation, which was to improve the structure of the code. The compiler got big and it got complicated. All these stages were using the same data structures. They knew too much about the internals of each other, and they were too coupled. So So that was a secondary motivation. In an open source project, it's important to keep the code accessible, maintainable. So that was a secondary motivation. Now, the third, flexibility, was not a motivation to do this work, but it could be an outcome of this work. And I'll talk about a little bit more what we might be able to do with this flexibility. So I want to convince you that improving the structure of the code of the compiler was a worthwhile effort. And my point here is the compiler is a significant part of the Python code base. In 3.11, if you look at the largest files in the interpreter implementation, the largest is Python AST, which is the parser. I grayed it out because that's an auto-generated file. It's not something we wrote by hand. So this is generated from a grammar definition, which is about 1,500 lines. So that doesn't really count as a lot of code. The compile.c, which is most of the compiler pipeline, not all of it, but most of it, that was the second largest file, and that's the largest handwritten file that we have in the interpreter. C-eval.c, that's the main loop of the interpreter. That's a big switch statement with a case for every bytecode and a bit of code to implement that bytecode. So that's a big file as well. And there's been some work to help that become more maintainable, unrelated to what I'm talking about. So, you know, that compile.c became simpler. Each stage uses a simpler data structure. It doesn't know about the other stages. That is good news for people who want to contribute to Python. This code is more accessible now. Now, why did this happen now? It came up now because these are the commits per month in compile.c since the end of 1990, when Python was first committed. And if we look at the spikes, so I kind of looked at the commit log, what were these spikes about? And so we see this big one now is the lead up to Python 2, the first big one. So there was some changes to the language, new features. So, you know, there were changes to the compiler, obviously. Then we have another kind of spike when nested scopes were added and the sim table. So nested scopes is if you nest a function inside another function and you can, from the inner function, access the locals of the outer function. That's when this was added in about 2001. The symbol table that's an internal change in the compiler. It simplified some optimizations. So that happened about the same time. Then we have a spike for the unifying long and int, and around the same time source code encodings. Then we have a spike for decorators, and that's also when the peephole optimizer was added. So another spike of activity. And you know, and so on. That's how it goes. And then async comprehensions and generators, another spike. But the last few years, that's not a spike, that's like mayhem, right? So what happened? Yeah, we had a few new features. There was pattern matching, there was exception groups, but a new feature doesn't cause that. A new feature causes a little spike like you see here. What happened in the last few years is that there was this huge push for performance. So there were the adaptive interpreter, a lot of other optimizations, just a huge focus on performance. And that created a lot of kind of a lot of activity on the compiler for a while. And it created the need to be able to test stages of the compilation process. So when you add something like pattern matching, how will you write unit tests? You will write tests that you write some pattern matching code in Python and you run it and you see that the output is what you expected. That's the unit test. You don't go and ask what did the optimizer do or what did the code generation do in this stage. You don't really care. You just want the whole thing to work. When you write a test for an optimization, you obviously want all the functional tests to pass, but you want your test to verify that the optimization is doing what it's supposed to be doing. And you can't really do that with a functional test. You can break the optimization, you will never know unless you have that unit test. So this is where it got awkward, and I'll come back to this later. So I'm going to walk through the whole pipeline now, all the stages, the old ones, the new ones, and just each of them, like what it does, just, you know, just so maybe not everybody knows all the stages. So I'll go over the old ones as well. So the tokenizer is exposed in the tokenize module. This is the part that takes the source code. The source code is just a string of text. And the tokenizer divides that text into tokens. These are the basic elements of the language. So the print is a name. It recognizes print as a name. There's no point breaking a print into smaller substrings. There's no meaning to them in Python. So it says we have a name here, print. Then the second token will be the open parenthesis, right? And that's an operator. And then we have a string. That's a string constant. So that's a token. So and then close parenthesis. So in our string, in our program, we have 4 tokens. And that's what the tokenizer does, and it adds something in the beginning, something in the end. But you basically get this list of tokens. You get, for each of them, the type, the string, and where exactly in the source code it is, which line and which column in the line. The second part, the parser, that takes the tokens and produces the abstract syntax tree. So this is implemented in the AST module, in the standard library. You can ask the AST module, ast.parse, to give it a string. It will give you an AST for that string. In our case, it's the tree it's an expression. It's an expression, the root node, because the whole thing is an expression, and the value of the expression is a call, and the call node knows what it needs to call and what arguments it needs to pass to whatever it's calling. So that's the second part, AST. And then if you remember the compile function from the beginning, we gave it a string and it compiled the string. You can also give it an AST rather than a string. So you can parse the string with the AST module and then give it to the compile built-in function, and it will give you the code object as before, and you can run it. And this is where the flexibility I was talking about earlier. This is a feature that people use. There are applications where they bypass Python's parser. They'll build their own, construct an AST somehow and compile it. Or they might use AST parse, get an AST, and then modify it, and then compile it. So this gives people flexibility to use parts of the compiler pipeline and replace other parts. Now, this compile of an AST, this is what I broke up into substages. So now we come back to, this refactor of the last few years, and I'll go over the new steps, what each of these steps does. How do we go from an AST to a code object, to bytecode? I'm going to run through the steps with this example. Imagine we have this code. We have a for loop for x and c, and in the body, if y, assign 1 plus 2 to z. Okay, that's our code. The parser will give us this AST. There's a for node. It knows what the iterable is, that's c. It has the target variable, that's x, that's the variable we're iterating with. Then in the body, we have the if statement, if y, then an assignment of 1 plus 2 to z. Yeah? That's what this tree says. So the first step was AST optimization. And this is where the optimizer will look for things like this subtree, and it will say, okay, this is a constant expression. I can just calculate it now and simplify the tree a little bit. So it's that kind of stuff happening at this stage. So it will change it. We'll have assign 3 to z. Now we have this optimized AST, and we come to the code generation stage. Now we're moving from an abstract syntax tree to something that is kind of like bytecode, but not quite. So this is the pseudo instructions. So if in this case, the for loop becomes we load C, that loads the iterable. The next instruction turns the iterable into an iterator, creates an iterator for that iterable. Then we enter the loop. For iter tries to get an element from the iterator that's at the top of the stack. If it fails, it jumps to the label L1, that's exiting the loop. If it manages to get something, it puts it on the stack, that gets stored into the local variable X. Now we go to the body of the for loop, load Y, check its value, this is the if Y, and then if we didn't jump over the body of the if statement, we execute it, otherwise we reach the end of the loop and we loop back and repeat. Okay, that's our for loop. So that's pseudocode for a for loop. Now, the next stage is the optimizer, the peephole optimizer. And the optimizer takes pseudocode and produces optimized pseudocode. So in our case, it will find that this jump that jumps over the if statement lands at the end of the loop and immediately jumps back to the beginning of the loop. So it's a jump to jump. So it says, okay, just jump to the beginning of the loop, don't jump to the end and then back, right? So that's one optimization that the optimizer can do. Now, there are many other optimizations. This is kind of probably the most complicated part of the whole compiler. So there's a large number of optimizations that can happen. This is not even the most sophisticated, but it shows it as an example. But this is the kind of things that can happen here. Now, finally, now we have optimized pseudocode, and we have the last step is the assembler that will take the optimized pseudocode and turn it into actual bytecode. And then it will construct some metadata, like the exception table, the line number table, all kinds of other things that a code object has, and it will construct a code object with all that. So now the differences between, there are a number of differences between pseudocode and actual bytecode, but jumps have a lot to do with it. So in pseudocode, the jump targets are kind of logical labels. Yeah, we have kind of jump to, here the argument is, in the pop jump if false.among, the argument is 3, and that is the index of the instruction in the instruction list. So, and in the actual bytecode, it has to be a relative offset. So how far should we jump? Right, either backwards or forwards. And another thing is that in pseudocode, the jumps don't have a direction. In the actual bytecode, a jump is either a jump forward or a jump backward. So when the assembler emits the code, it figures out the direction of the jump and decides which jump instruction to use, because there are no negative offsets. And in this case, you see that we turned a pop jump if false, a conditional jump, into a conditional pop jump if true, followed by an unconditional jump backwards. And this is because the actual bytecode doesn't have conditional jumps backwards. So all conditional jumps go forward. And if you want to jump backward, you have to do it with an unconditional jump. So a conditional jump backward has to be translated into this sequence. So that's an example of what happens in the assembler stage. So now we have bytecode. Now, I told you what each stage does. I didn't tell you how to access it from the standard library, and that's because it's not officially part of the standard library, not yet. These functions are currently exposed in a module that is called test internal CAPI. So that is, underscore test internal CAPI. The underscore tells you it's none of your business what's in there. This is a test module that we use. And I think maybe we want to expose these functions in the standard library, like the tokenizer and the AST module and so on. That will require a PEP. We will have to have a discussion about what exactly are the use cases and in what form do we want to expose this, and what kind of stability guarantees do we want to attach to it. And we haven't had that discussion yet. So, and I'm not going to kick it off unless there is kind of interest and there are use cases coming. So the ball's in your court on that. Like if people come up with use cases and they are compelling, then it could happen. Now, in the meantime, we use it for testing. That was the main kind of motivation for this. So let's look at that jump-to-jump optimization that we had. We had for X and C, if condition, whatever, some code block. And we know that that creates a jump-to-jump, and the optimizer removes it, right? Because we saw it a few slides ago. And if we want to write a unit test for that, well, in 3.11, when we wanted to test it, this is what we did. We wrote this code in Python. We gave it to the compile built-in, got a code object, gave that code object to this disassembler. Yeah, there's a dis module. You can give it a code object. It will give you some representation of the bytecode, and then we asserted that there's no jump-to-jump there. That is not a test that we should be proud of. This is not a very good way to test this, because how do we know that there ever was a jump-to-jump? How do we know that this test really is testing what it's supposed to be testing? If somebody changes the compiler and now this pattern doesn't generate a jump-to-jump anymore, we will never know. This test will just stop testing what it's supposed to be testing, and we will never know. So that optimization won't be covered by any test, and we will have no idea. So now in 3.13, the test is written like this. We write the input as some kind of sequence of pseudo instructions with logical labels. And we write the expected output, and we run just the optimizer, not the whole compiler, tokenizer, parser, compiler, and then disassemble. No, just run the optimizer, see what it does, and assert that the output is what we expected it to be. And we have similar tests for the code generation stage and for the assembler stage. So we have all three stages have their own kind of test harnesses that we can write these tests very easily. And another little toy that I've been building, now this is the first GUI I ever implemented, just so you know. So I expect kind of support, but so I wanted to build this, and I'm really hoping someone will kind of save the world from me and take it on. But I think it's kind of nice to be able to put a little piece of code and see all the stages of the compilation process in front of you, just like that. So, yeah, you have the link, so go fix it. So, yeah, that is the story of the Python's compiler pipeline in version 3.13. Thank you.
Thank you so much, Irit, for a great talk. We have time for a few questions. If anyone does, there's a microphone right in the center, if you could go there. Put the link back up there.
Oh, yeah. Please do, yeah.
Has anybody started working on it yet? Could you go to the microphone, please? Oh, sorry. Go ahead.
Oh, I go first. Okay. I just want to ask, are there unit tests that are now possible due to this refactor? Are they written in C or Python?
They're written in Python. I mean, yeah, all our unit tests are written in Python with the test internal CAPI module. These are kind of these are hooks to get into the CAPI from Python.
I'm wondering, is there a catalog of what optimizations are implemented currently and or anything that's sort of in the works and coming soon?
We just, read the code. Yeah. I mean, the tests. Yeah.
Thanks.
Yeah, no. I guess that was a no.
Thanks for the talk. Great talk. I was curious, do you think we could take this a step further and break apart the compiler itself so it's more customizable? So like if you want to build an alternative Python compiler that compiles, say, functions differently, you can hook in and just do that differently and still borrow the rest of the compiler from CPython.
I'd love to if my boss gets on board, yeah.
Anyone else? If not, thank you all very much. A big hand for Irit.